Welcome back to the continuing series on AC networks. This is part 3. Right? We know that all network combinations of R, L, and C circuits can be solved with differential equations, and we've seen that in part 2 and earlier on with our classroom work on DC circuits, meaning the forcing functions with DC voltages or DC currents. But we may run into a problem with differential equations because we can end up with situations which requires simultaneous equations of differential equations, which we will have to resolve, and this can be tedious, time consuming, and easy to make errors. So an easier way is to use the superposition principle. With the superposition principle, with a forcing function V1 corresponding to a current I1 of t and a forcing function V2 of t producing a current I2 of t, using superposition principle, we can form a general forcing function and simply call it V of t, where V of t is equal to V1 of t, sum of that, plus V2 of t. Right? That is our superposition principle. So V1 of t corresponds to Vm cos of omega t, which, as I've said before, we solve using differential equations. But now we are going to find an easier way to resolve it, and that is using complex algebra, right, or complex notation. Now, Euler's form has got a lot to do with this, particularly in his formula e to the power of j theta equals cos theta plus j sine theta. Which I call equation 2, and e to the minus j theta equals cos theta minus j sine theta. Right. Just to remind us, what is j? J is equal to I, the imaginary number which we come across in pure maths. Now, this was a problem for the ancient Greek mathematicians, right? Because they could not use real numbers to solve x squared plus 1 equals 0. So they were left in the lurch and the whole world at that, for over 1,000 years, until a clever mathematician came up with, well, if you can solve it with real numbers, let's create imaginary numbers. So he said, well, I squared is equal to j squared is equal to -1. So therefore, I, which is equal to j, is equal to square root of -1. Right? So mathematicians use I, engineers use j. So we, as engineers, will be using j. Now, back to the Euler's formula. If we add equations 1 and 2, we'll define cos theta. It is equal to a half into e to the j theta plus e to the minus j theta. And equation 1 minus equation 2 defines sine theta, which is a half 1 over 2j, into e to the j theta minus e to the minus j theta. Right? If we apply this on our forcing function v of t, we can now rewrite v of t as being equal to Vm e to the j omega t. And I'm just reminding you here that this omega t here is from the theta at the top there. So when we expand that on the basis of Euler's formula, so it's Vm cos omega t plus j sine omega t. That is j. Now, V1 of t takes the real part of v of t. So it must be the real part of your forcing function. Right? And the real part of that is your cosine component, cos omega t. M cos omega t. Now the solution will be of the form I of t equals capital I e to the j omega t, which is also written as I exp of j omega t, where I is equal to the modulus of capital I e to the minus j phi. Right? Remember e to the minus j phi, back to Euler's theorem, Right, so using that, we can simply expand I of t is equal to modulus of I e to the minus j theta multiplied by exp j theta, which is e to the j omega t, and that is equal to modulus of I e to the j omega t, combining the exponents, it is omega t minus phi in bracket times j, and using Euler's theorem on this, that bit there becomes, it's like your theta, so it's simply modulus of I into cos of omega t minus theta plus j sine omega t minus phi. So the real part of the forcing function Vm e to the j omega t is the real part of I of t. Right? And I of t, as you can see, I1 of t is equal to the real part of I e to the j omega t. So it is equal to the real part of modulus of I e to the j omega t minus phi, which is what we have over here. Okay? So you can see in here, the real part of this is simply the real part of this, and the real part of this is just this, because over here we do not have any j, whereas the sine bit in here is multiplied by j, so that is not real. So this is the only real part, so that is why it is reproduced down here. Cos omega t minus phi multiplied by the modulus of current. Remember, reminding you, phase angle phi. Right, now that we've discussed how to resolve this using complex algebra or complex notation, let's apply this then to the RL circuit that we had initially, right? Reproducing here, reminding you again that we applied Kirchhoff's voltage law, VL plus VR equals Vm cos omega t, equation 2, fundamentals, which is L di dt plus Ri is equal to Vm cos omega t. Now, if we use this complex notation, well, everything on the left is the same, but the right becomes, instead of Vm cos omega t, it's Vm e to the j omega t. So I've labeled that as equation 2 star. Now, the real part of the solution. Right, first, we've got to consider the particular integral. Right, because of the right-hand side, right, the way that the right-hand side is, we've got to, the particular integral has got to be in a similar form. So I of t is equal to I, capital I, e to the j omega t, equation 7. We differentiate I, di over dt, j omega I, e to the j omega t, equation 8. Then we look back at equation 2 star. So we simply take L di dt is represented by this portion here, and Ri is represented by that portion there, and it is equal to the forcing function, same forcing function which is down there. I've circled the common factors in here so that we can divide throughout by e to the j omega t, cancels everything. So the only factorize the left hand side, I common factor into R plus j omega L equals Vm. Reminding you again, remember Ohm's law, where V is equal to I times impedance. So that bit in the bracket there is our complex impedance. Right? So I, from here, making I the subject of the formula, is just Vm over R plus j omega L, and the modulus of R plus j omega L is the square root of R squared plus omega all squared, multiplied by e to the minus j theta. And where e to the minus j phi, where phi from a right angle triangle in the last part 2, is the inverse tan of omega L over R, and also equal to inverse tan of XL over R. So that gives us our final solution as I of t is equal to the real part of I e to the j omega t, which is equal to Vm divided by r divided by square root of r squared plus omega L all squared times cos of omega t minus phi. That, guys, brings us to the end of part 3. Look forward to the next one. Have a good day.